Okay, good afternoon. So we will be having very brief lecture, and if you recall, before the mid-semester exam, we have started our discussion on the vapor absorption refrigeration system. And while we are talking about the vapor absorption system, we are having one refrigerant and one absorbent. Okay. So whenever refrigerant mixes in the absorbent, then finally whatever the homogeneous solution we get, that solution is having certain composition. Okay, and we tried to see the temperature composition diagram and enthalpy composition diagram, particularly for the mixture of water and ammonia. Okay, so while discussing these type of systems, I explained you about the enthalpy composition diagram, and we discussed about three different processes. First process was adiabatic mixing of two streams. Okay, and the streams which we are considering, these are actually mixture streams. It means each inlet stream is having mixture of water and ammonia, and these are having certain compositions x1 and x2, and the corresponding enthalpies were h1 and h2. So in this type of situation, because my control volume is this one, and as the system is adiabatic, so there is no heat interaction with the surrounding. So the two streams, whenever these are mixing, these will give me the final mass m dot 3 as the sum of their masses, and composition at the inlet, which is m dot x1 plus m dot x2, will be nothing but equal to m dot 3 into x3. Likewise, whenever we will be applying the energy equation, then we will be having the same thing applicable for enthalpy. Is this one clear? After that, we have tried to see another different process, which is actually mixing with heat rejection. So typically, in the entire vapor absorption cycle, we saw that refrigerant comes out of the evaporator, it gets absorbed in the absorber, and in the absorber, during the mixing process, absorption process, we are also actually cooling the mixture. Okay, so that's why the process is mixing and then cooling. Why mixing? Because from one side vapor is coming from the evaporator, and in other side of the absorber, from the top I am getting saturated water, which is coming from the generator. Is this one clear? So for that purpose, my mass and composition equation will remain same. Only in the energy equation I will be having one heat which is going outside. Okay, and because of this we found that what we found, that if this is my process 1 to 2, then in adiabatic mixing my point would have been at 3 dash, but in real scenario QA by m dot 3 amount is actually being rejected, so that's why enthalpy will be coming to 0.3. Is this one clear? And after this, I was explaining you about this process, and then we couldn't complete it. So the process is cooling and separation. What is the meaning of cooling and separation? Please tell me. This is state 1, and state 1 is my which state? Saturated vapor state. Then what I have done, I have rejected certain amount of heat. If I am removing certain amount of heat, then what I will be having? Decrease in enthalpy at the constant composition. So here this is state 2, where composition, if x1 is composition here, x2 will be nothing but equal to x1. Overall mixture composition will remain same, because I am not adding anything, I am not removing anything over here. But after this point, what I have done, I have separated in a tank the liquid and the vapor phases. Okay, so this is very clear to us, because at the inlet I have saturated vapor. So if I have saturated vapor at the inlet, when I will be cooling, what will happen? I will be having a two-phase mixture. Okay, and if I put two-phase mixture inside a tank, liquid will be settling at the bottom and vapor will be collected at the top. So that is the process. So this is my enthalpy composition diagram. This is point 1, which represents x1 composition and h1 enthalpy. I am cooling point 1. So if I am cooling point 1, my enthalpy should decrease, whereas the mixture composition is remaining same because I am not adding anything into this first chamber. Okay, from outside I have neither added ammonia nor added water, nor I removed both of these components. So composition should remain same for mixture. So that's why at same x1 equal to x2, after cooling I will be having some point over here, which is my point number 2. Okay, then after 2, what I have done, I have put everything inside a chamber, and there the liquid and vapor are segregated. Okay, so once I have segregated liquid and vapor, I need to go to saturated liquid line and saturated vapor line to represent the state of this portion and this portion. Is this point clear? So that is why what I have done, you tell me what I have done. I have drawn a isotherm such that it is passing through point 2, because the temperature of this vapor is also T and temperature of this is also T. As a mixture, both are having same temperature. So it means that I should draw isotherm over here. Now at the top I have pure vapor, at bottom I have pure liquid. At the given pressure, pure liquid is represented by this line because it is saturated liquid line and it is saturated vapor line. So pure vapor at that temperature is represented by top line. Okay, so where this isotherm is crossing, these are my points 3 and point 4. Corresponding to point 3, I will be having composition of 3, and corresponding to point 4, I will be having composition of vapor. So it means, someone waiting outside? So whenever we are having actually 3 and 4, what it means? It means that when mixture is separated, the composition of liquid and vapor is different. Is this point clear? Now you can see one interesting thing, which is even leading to some physical conclusion. What is the composition of liquid? X3. Very less, because this is for, on this diagram, this side is this is actually X of ammonia. So what it means, here ammonia is 0, here ammonia is 1. Okay, so when I am having very less value of ammonia, what it means? What is the meaning? Composition of ammonia in the liquid is very, very less. Here composition of ammonia in the vapor is significantly large. Okay, so it means upon cooling I can separate out the mixture. Okay, now what should I do? I have gone to this, then I am at point 4. From point 4, if I again do a next cycle of cooling and separation, what I will be getting? In vapor I will be having composition of towards the higher side, and here composition will be again in the lower side. So it means this cooling and separation process can be employed for extracting the pure substance out of the mixture. Is this point clear? So cooling and separation can be employed for separation of the pure substance from a mixture of two substances. Is this point clear? Now one small process we will discuss. After that, in the next class we will solve the complete numerical problem. And process number 5 is throttling process. What is throttling process? It is expansion process also we call, and it's nothing but isenthalpic process. Okay, so for single phase substances we simply know that in a throttling process what happens? Pressure decreases, and if we are operating on left side of the inversion curve, then temperature also decreases. Is this one clear? And for refrigeration applications we have to operate always in the left side of the inverter. Okay, now one interesting concept I discussed, I had explained you about generator. Okay, at the bottom of the generator I was having actually water in ideal condition, but in real scenario I will not be having pure water. Along with the water I will be having certain amount of ammonia. So when this ammonia and water mixture will be passing through the throttling process, and then it will be entering into the absorber. So what happens when a mixture passes through the throttling process? That is what we want to understand. So let me consider that this is my enthalpy composition diagram. First you tell me, and this is at some pressure P1. First you tell me at the inlet of the throttle I will be having nothing but saturated which state? Saturated liquid. Okay, saturated liquid state. So I am on saturated liquid state with some composition X1 having enthalpy H1. All are clear with this point? Now when I am moving through the throttle at point 2, what will happen? H2 will be same as that of H1. And what about composition? In the throttle, have I added any ammonia or removed any ammonia? No. So composition should also remain same. It means point 1 and point 2 will be represented by same point on the enthalpy composition diagram. However, one interesting point you have to note down, at point 2 pressure is P2 which is less than P1. So it means that for P2 pressure I will be having over here separate saturated liquid and saturated vapor lines which will be slightly downward. So this is for P2, this is for P2. Now with reference to P2, point 2 is in which line?
How do you know that point 2 is
Because for point 2 pressure is less.
pressure is less, but can it go above P2? How will you do this?
Because at the inlet we are already ensuring that we are supplying saturated liquid. Okay, so inlet is controlled. Is this point clear?
But after you boiling total boil, whatever is happening, it's something like vapor.
It is liquid plus vapor always. Saturated liquid, when you throttle, flashing happens and it makes mixture of liquid plus vapor. Okay. Is this point clear? So point 2 over here for pressure P2, it is in which regime now? Two phase regime. Is this point clear? So for obtaining the property of this point, what I need to do? If I have to find out the temperature, what I need to do? I need to draw multiple isotherms, and the isotherm which is passing through this point, that will be representing my temperature. Okay. Okay, so this is all about throttling process. Now we will discuss in the next class.